Welcome to this explainer. Okay, so today we are unpacking one of the absolutely most fascinating technological competitions of our time, the race to build scalable quantum computing hardware. If you follow this space, you already know there's a massive shift happening right now. We're officially moving past the theoretical physics chalkboard and diving headfirst into building gritty, physical machines that can actually handle complex, world-changing computations.
So, let's dive right in by acknowledging a pretty wild reality. In quantum physics, almost anything that can alternate between two well-separated energy states can technically be used as a qubit. Atoms, ions, photons, electrons, they literally all have their dedicated backers. But the real prize, the ultimate goal everyone is desperately chasing, it's scalability. Because, building a handful of qubits in a lab is one thing, but engineering a system that can actually grow is an entirely different beast. Now, to really grasp the current landscape, we've got to talk about quantum dots. In practical terms, think of these as nanoscale traps. They're really precise wiring and electromagnetic interactions that can grab and hold a single electron in a microscopic patch of silicon. Once it's trapped, we can use that electron spin, up, down, or a superposition of both, as our qubit. The reason this matters so much right now is that current systems are seriously struggling to scale up. To do the highly complex math quantum computers promise, we don't just need a few qubits, we need thousands of high-quality qubits.
All right, here is our roadmap for today. 1. The scaling challenge. 2. Contender 1, silicon dots. 3. Contender 2, moving electrons. 4. Contender 3, diamond defects. And 5. The race to scale.
Section 1. The Quantum Scaling Challenge. Engineering over physics.
Section 2. Contender 1, silicon dots. So, as this whole battleground shifts from theoretical physics over to practical engineering, our first contender, HRL Laboratories, comes in with a massive advantage. They're using manufactured quantum dots, which can be built using the exact same technology and infrastructure we already use to build traditional silicon processors. And that's a huge deal because, well, we already know exactly how to manufacture silicon at a massive scale.
This brilliantly illustrates the massive shift HRL is proposing. The old way of managing these electron spins involves hitting them with microwaves, and that requires separate control systems and tons of bulky cabling running all the way down into a super-chilled refrigerator. But the new way? Fully electronic wiring. HRL uses 3 adjacent quantum dots, and by controlling how the electrons interact, they can change their spins. They rely on the Pauli exclusion principle, basically the rule that no two electrons can have the exact same spin. Think of it like atomic orbitals filling up like seats on a bus. Each seat holds a spin-up and a spin-down passenger. By controlling these interactions electronically, HRL eliminates the need for those bulky microwave cables entirely.
Now check out the sheer efficiency of HRL's controller. Because they ditched the microwaves, they were able to build a traditional low-temperature processor to sit right inside the refrigeration system and manage the qubits. Even though it's built on an older 130-nanometer manufacturing process, it consumes less than 3.5 watts of power. To put that in perspective, that's less than a standard LED light bulb. It just receives compiled instructions from the outside and then operates completely autonomously, communicating with the qubit chip via a simple superconducting ribbon cable.
And the results are incredibly promising. In a demonstration using 18 qubits, HRL ran a simple error correction code and achieved a logical error rate of less than 1%. This is a massive deal, seriously. It's well below what other technologies have achieved at this stage, and it firmly validates their approach. It basically proves that their remaining challenges are just engineering problems, not fundamental physics blockers.
The industry absolutely took notice too. In fact, IBM actually bought this HRL technology. Now, IBM has historically bet big on a totally different tech called transmons, which use those exact microwave pulses that HRL avoids. But as Jake Mbetta, IBM's director of research, points out, both approaches are built on silicon. So buying this tech gives IBM massive enterprise flexibility. Some quantum architectures are better for memory, others for creating magic states. IBM now has the foundation to run both in parallel. That shows incredible confidence in the flexibility of silicon-based quantum dots.
Section 3. Contender 2, moving electrons.
Looking over at Delft University of Technology, we first really have to understand the architectural problem they're solving, what's often called the wiring trap. Normally, manufactured qubits, like the ones on a silicon chip, are physically trapped by the geometry of the wiring around them. You can't just connect qubit A on one side of the chip to qubit Z on the other side unless there's a physical wire there. Because error correction codes rely heavily on this physical geometry, you have to lock in your algorithm during the manufacturing process. If someone invents a much better error correction code tomorrow, well, your physical chip might be totally useless. You lack algorithmic flexibility. Delft solves this limitation with a highly creative, almost playful workaround. They literally created a microscopic bus route right on the chip. Step 1, the single electron starts at a quantum dot. Step 2, it physically moves along a 1.2 micrometer track to neighboring unoccupied dots. Step 3, it can be stored at a sort of bus stop or brought right up to another electron to be entangled. By actually physically moving the qubits around the chip, any two spins could theoretically be connected. That offers the kind of incredible algorithmic flexibility you usually only find in neutral atom or trapped ion systems. And it works remarkably well. The Delft team reported that the fidelity of sending a spin from one end of this bus route to another and back is nearly 98%. Now, it's important to be clear, noise during the spin exchanges and the loss of coherence while the electron is just idling at a bus stop, those remain hurdles that definitely need engineering solutions. But the proof of concept for dynamic, movable, manufactured qubits, it is undeniably there.
Section 4. Contender 3. Diamond Defects.
Over here, a company called Saxon Q is taking a completely different, honestly kind of sci-fi approach. They're using the crystalline structure of diamonds. The core of this technology revolves around something called a nitrogen vacancy. A diamond is this highly regular array of carbon atoms, right? But if a nitrogen atom gets trapped in there as an impurity, it forms one less bond than the carbon normally would have. That leaves a neighboring carbon atom with a single unbonded electron. And just like a quantum dot, the spin of that lonely electron can be manipulated as a qubit. Now, placing these vacancies used to be basically random, which meant bespoke, unpredictable chips. But Saxon Q developed a breakthrough technique to place these nitrogen vacancies precisely within a 10-nanometer radius, exactly where they want them. So the absolutely crucial point, the thing that makes this approach a real game changer, is the operating environment. Because of the incredible stability of the diamond lattice, this technology completely ditches absolute zero refrigeration. It literally operates entirely at room temperature. It fits inside a standard IT server rack mount, plugs right into a completely normal power supply, and is built on modular cores containing 8 qubits each. You don't need some massive multi-million-dollar cryogenic lab to run this hardware. The whole shebang can just sit in a server room. And they aren't just theorizing this for down the road. Saxon Q is already selling modular units containing over 100 total qubits, which they achieve by integrating multiple cores into a single rack. They actually expect to begin shipping these units within a few months, with even larger systems slated for next year. Even though a 100-qubit system is currently a bit too small to run major error-corrected computations, the quality of the hardware itself is staggering. Saxon Q reports that their individual hardware qubits achieve a remarkable gate fidelity of over 99.9%. That makes this room temperature technology incredibly competitive with the massive, super-chilled mainframes being developed by the giant tech companies.
Section 5. The Race to Scale. So, zooming out, we can really synthesize these three wildly different engineering solutions that are all trying to crack the exact same scalability problem. HRL and IBM are using silicon dots to eliminate messy microwaves and scale up using traditional chip manufacturing. Delft University is giving manufactured chips the ultimate algorithmic flexibility by literally creating microscopic electron bus routes. And Saxon Q, they're throwing the refrigerator out the window entirely, utilizing diamond defects to run highly stable qubits right out of a standard server rack at room temperature.
As we watch quantum computing transition so rapidly from the realm of theoretical physics into the gritty, practical world of physical engineering, the landscape is just more exciting than ever. We aren't just hoping quantum computers are possible anymore. We're literally watching different factions build the tracks in real time. So the question I want to leave you with today is this. Looking at the sheer ingenuity of these distinct approaches, which of these incredible breakthroughs will ultimately cross the finish line first and crown the era of the true scalable quantum computer? Thank you so much for learning with me today, and keep your eyes on this space. It is moving fast.